tell us all about the sun.
Hi everybody, my name is Katie Whitman. I'm a physics grad student at UH, and I've been on this stage many times, but usually behind the drum set or like as a promoter or something. I've never been up here and talked about science. And also, I've never had a beer before talking about science in front of people. So this is a couple of new interesting things. So, all right, I'm going to talk about the sun, that fantastic ball of plasma in the sky. Okay. So, it turns out that this talk is the kickoff to Global Plasma Month. So, what the heck? So, the Nerd Night organizer in LA, in honor of plasma, he loves plasma, it's his thing, he organized many people to speak all across the country and even in a few international locations about plasma. And it turns out that Honolulu will be the first talk for all of February for Global Plasma Month. All right. So, but why would plasma get its own month? Okay, so, my drinking game. I couldn't really decide in a drinking game. If I said plasma was the word, you would just be wasted. Same with sun, magnetic fields, I don't know. So I decided if you just see something that's beautifully amazing, and in honor of that beautifully amazing plasma thing, you can just take a drink. Okay. All right, so that being said, why plasma? All right, because this, because this, because this, alright, and because what I want to talk about today, about the sun, alright, this is a super high-res, beautiful image of the sun. Okay, so first of all, what is plasma? I thought the Nerd Night flyer had the plasma donation mobile, but that's a different kind of plasma. That's the biologist kind of plasma. I'm talking about the physics kind of plasma. So, what did you learn in high school or whatever? Not physicists, don't answer this. There's a few physicists in the room. What is plasma? What did you guys say? What was it?
State of matter.
The fourth state of matter. Okay, and does anyone know what that actually means? Yeah. Everyone always, plasma is the fourth state of matter, but no one knows what it means. Okay, so let's take a look. This is my representation of atoms right here. We can pretend these are atoms in the air, oxygen, nitrogen or something, and you can see it's a balmy 75 degrees, say it's nice room temperature air. And all of our nuclei are together with our electrons. So this is our atomic nuclei and the electrons that orbit around them. But if we add energy, and we can do that by adding electricity, we could add heat, or we could even send something in to collide with our atoms. And when we do that, we can actually take the electrons off of the nuclei. Okay, that's called ionization. So we can ionize all our atoms, and we can make this soup of charged particles, okay, a charged gas. So let's take a look at the components of our plasma, all right? If we look at each component, we see that we have little charges, charged nuclei, and we can bother Garfield with them or whatever, but there are little charges that make up our gas. But for the most part, if we look at the, Firefly fans in the house. Okay, so if we look at the gas, the plasma as a whole, in general, it's still neutral. There are equal numbers of positive and negative charges. So there's a lot of plasmas in space, and they're still overall neutral, but the components are charged. All right, so where do we find plasmas? It turns out that a lot of the matter in space is actually plasma. So here we have a whole galaxy, an active galactic nuclei, and we see some jets coming out. And these jets, the only way we can see them is because there are charged particles getting shot out from the center of this galaxy. And that's plasma. So here we have the crowd pulsar. All right, that's That is a neutron star spinning, and it has a lot of energy in it, and it gives some energy to the gas around it. It makes a plasma. Okay, here we have the Eskimo Nebula, because apparently it looks like a head with a parka around it. Okay, so there's a star in there. There's a star in there that's putting energy into the gas all around it, and that makes plasma. And then we have the Orion Nebula, and this is where stars are born, because this is a birthplace of stars. And all those new stars glow really brightly in ultraviolet light, and that will also ionize the gas around it and make plasma. So there's plasma in many different places around the universe. Okay, so what is super special about plasma and why it matters so much? Well, it turns out if you take charged particles and you stick them in with magnetic fields, they interact. So in this case, we have a magnetic field. So now there are going to be a bunch of lines and arrows in many of these diagrams now, and those are all going to be magnetic field lines. They're going to show where the magnetic fields go. If we take some of these charged particles and we send them in to the magnetic field, they like to circle around them, okay? And you can kind of see they go in opposite directions. Positive goes one way, negative goes the other. Now, if we take our charged particle and we give it some velocity along the magnetic field line, it'll actually spiral all around. It gets stuck on the magnetic field line. It follows where the magnetic fields go. So, lots of things in space have magnetic fields. The Earth has a big magnetic field. And it turns out that there's a bunch of charged particles out there. There's like a whole population of charged particles that are stuck on our magnetic field lines, and they just bounce back and forth and back and forth and back and forth. Okay, so magnetic fields and plasma goes where magnetic fields say they should go. Okay. All right, so let's look at what happens on the sun. So the sun has a magnetic field. It's even more complicated than the Earth's magnetic field, and the sun is also very hot. There's a lot of energy there. So basically everything there is plasma. Everything is charged particles and lots of magnetic fields. So we could get super cool things happening up there. Okay. I love these videos. This is from a satellite called TRACE, and it's called TRACE because it wanted to trace all the magnetic fields on the sun. Luckily, thanks to plasma, the plasma flows along the magnetic fields and we can see what's happening on the sun. All right, next. This is one of the coolest videos to me. There's some kind of flare, something, I don't know, but this gigantic canyon opens up on the sun. And all of these magnetic fields start popping up through the surface. And the plasma flows along them. It gets all excited and glows. Okay?
Drink.
Super cool. Yeah, come on. Can we get at least a drink for that? All right. Next. All right, so this is just to look at the sun. You guys are probably used to seeing the sun look like this, right? That's the sun in visible light. And sunspots in visible light look like dark blotches. But you can also take pictures of the sun in other filters. Like you put a different filter on your camera and do like cool infrared shots of plants to make them look white or something. Well, you can take ultraviolet pictures of the sun, and when you look at the sun in ultraviolet, all of those dark sunspots are suddenly intensely bright. There's so much energy around these sunspots. So all of these bright spots here are where you see sunspots. And this here are magnetic field lines. Okay, this is a representation of what's going on in the sun. So this is super cool. That's what a sunspot looks like close up. It turns out this right here is about the size of the Earth. Okay. A lot of cool things going on. So what a sunspot is, it's like a magnetic knot going through the surface of the sun. And because the magnetic field is all knotted up, all kinds of really cool things can happen. So some of those cool things, the things that I like to study, are flares and coronal mass ejections, all right? And a lot of people don't know the difference between the two. But a flare, so there's an explosion on the sun, and that energy is released in electromagnetic form, electromagnetic energy. That means light. Okay, visible light, X-rays, gamma rays, ultraviolet. That's the flare. Usually following the flare, often following the flare, you get a coronal mass ejection. That is a bunch of plasma and magnetic fields ejected from the sun. Okay, so this is a big ball of plasma ejected from the sun into space. So this is a close-up of what a flare looks like right here. That's one flare, and this is the second flare. And these are those cool loops forming like you saw in the other video. You kind of see something gets shot away, right? So you can't see it real well on this filter, but those were coronal mass ejections getting shot off after the flare. And they disturb all these magnetic fields on the sun. So they make them move around. They're like little elastic bands that get moved around. Okay, so this is from a movie called Solar Max. I can do it. Okay. These are just coronal mass ejections getting shot off of the sun during solar maximum. And it's just happening all the time. Just big balls of plasma getting shot off of the sun into space. And there's also this thing called the solar wind that comes out all the time too. It's just plasma flowing away. It's going a lot slower, it's a lot more gentler. It's only like 400 kilometers per second. The coronal mass ejections go like, I don't know, 800 to like 3,000 kilometers per second sometimes into space. So what will happen if the coronal mass ejection heads towards Earth? This is a nice video. Is this in? Zooming in. Suddenly we get this release of a coronal mass ejection. This is both plasma and magnetic fields heading towards the Earth. When it hits the Earth, because they're magnetic fields, they interact with the Earth's magnetic field. But luckily we have a shield. It's a shield. Most of this stuff goes around. But some things happen here, and it ends up energizing particles in the tail of the Earth's magnetic field, which follow the magnetic field lines down to the atmosphere. And where did the Earth's magnetic field meet the atmosphere? At the poles, right? Exactly. And we get aurora. Yeah, aurora is because of plasma ejected from the sun. Okay, so if we look at aurora from space, we can see really clearly that this is a phenomenon that comes from space. You can see kind of like streaming down. Oh, it's really cool. It's pretty cool.
Can we drink for coronal mass ejection?
Yeah. I second that. Excellent. So, this is the aurora from above. You can also look at the aurora from below. And you can see this sort of streaming behavior of particles coming down. And it has these crazy shapes because it's following magnetic field lines of the Earth. They move all around. They're like electric currents in our atmosphere. And this is actually plasma too. What happens, well, I can tell you in a second what happens. Wait a moment, okay. This is also very beautiful. And you notice these colors. This is Photoshop, what the heck? It's red and green, so beautiful. Well, actually those are real colors. I'm gonna go back to this one to explain this. Okay, so what happens is you get particles coming in from space and they smash into the atmosphere, they smash into some oxygen, they smash into some nitrogen, and they put energy into the electrons that are orbiting around those atoms. And so, in some cases, they make them fly off completely, which makes a plasma. In other cases, they just excite them to a higher level. And when they either recombine or drop down, they give off light. And they give off light in some beautiful colors. Okay, so these are the colors of the aurora. Nitrogen makes all these beautiful reds. Oxygen makes that crazy green color you see everywhere. Nitrogen also makes purples. Okay, so these are real colors of the aurora. And I think, okay, so let's put it all together. So if you understand about plasma, understanding plasma means understanding much of the matter in our universe, all so much matter in space is plasma. Our sun is made of plasma. Other stars are made of plasma. The environment in our solar system is just filled with plasma from the solar wind. Space weather, all those things that cause auroras, that actually is a radiation hazard for astronauts in space, or people trying to travel through space. They're in danger of getting hit with all of these energized particles. And satellites also don't like it so much when they get blasted with charged particles. There's our atmosphere. I showed one picture of lightning, but that makes plasma for a moment. The aurora, those are plasma. You can make, we're working on fusion energy devices. Fusion is the way that the sun makes energy. That big ball of plasma makes energy through fusion, and we're working on trying to do that too. And of course, if you can control plasma, you can make lightsabers. So, the best use of plasma. So, I'll leave you guys with this final image. Okay, thank you.
Yeah, y'all. Turn up at the top a little bit, y'all. You know, with the head is loud and clear, right now.